quantum computing courses, especially faculty development programs. I conducted the first one in 2022. And of course, from February onwards, we have been doing many courses. So all of these courses, except for QT-03, she has taught in all the courses till now. And her background is basically, she did her master's from University of Calcutta and Jadavpur University. And she was part of the, she did MTech Computer Science from University of Calcutta. Before that also she did from West Bengal University of Technology, to the government college in Kolkata. She did her undergraduation. She's presently pursuing her PhD from University of Calcutta. That is one. And apart from that, she's doing a management degree also from IIM Calcutta. And that is something which is very different. And then she was part of the QRD lab in Jadavpur University for some time. And that's where I think in 2022. Last 7.5 years, she is with PricewaterhouseCoopers, US R&D on quantum. So that's the core work that she's doing while she's doing her PhD, and she's completed her postgraduate executive program in business management from IIM Calcutta. Last year she completed, and then this year she'll be mostly completing her PhD, I think, in a couple of months. So without wasting much time, ma'am has been continuously teaching, so she is a very keen, interested person in quantum computing, and she's been an IBM educator as well. She was referred by IBM, so she's been trained by IBM to take these classes. So without wasting much time, we'll go into, ma'am will take the next 3 lectures, that is today, tomorrow, and day after tomorrow. So the next 6 hours of lectures will be by Ms. Nivedita Dev. Over to you, ma'am.
Thank you, sir. Yes, just a quick, I think, modification here. The QT lab, it was kind of incubated from University of Calcutta. It was not from Jadavpur University. Yes, so right now I am not like actively into it, but fortunately a lot of like researchers and students from University of Calcutta, they are taking care of it, also like from ISI and all, RTKGP, so they are working on that. So that is something that I wanted to say. And as said, so okay, there is a power cut here. I think there might be some shortage. I don't hope that happens here right now. Okay. And thankfully, like 3rd December, I completed all the convocation program and all that got over from IIM Calcutta. I worked on the generic medicine adoption. So mostly it was on a strategy management as well as policy. Okay, how we can map technology, including AI, into policy making. So we were working on that. So that got over. Every process is over. We are going to get that. I actually got that alumni status officially, and mail ID also I'm going to receive within a month. It takes some time for the executive education department to take care of it. So yes, so that's some good news that I want to share. Okay, I think on that note I can start.
Yeah, even the LinkedIn shows that October 2026 is where you are scheduled for your PhD, I think, right? So
Yes,
that's
yes. Yes, so I'm a mother of two, so like Dr. Philly
yeah.
knows about it, and also like PwC, it's very like fast-paced environment, a lot of technology, emerging tech. I have to work on that. So thankfully, my professor, my PhD professor, he's very kind of supportive person. So yes, so one SCI is one I'm looking into. So once that gets over, all the research methodology, all the work, courseworks are over, remaining criterias are over. So once I got that, I will be completing my thesis, and that is the plan as of now.
Yeah, surprisingly, she is working in blockchain, another area of my interest. But yeah, that is surprising. Quantum computing, AI, blockchain, so multiple
And
domains.
there also like one thing I want to here only introduce that I am very soon going to get into the detailed research of the technology management side as well. So there I have certain plans I will be sharing with you. And anyone, if you are interested, you can just connect me, because what I want to do is a blend of technology and management. It's not only about quantum, it's about quantum AI, cryptography, blockchain, IoT, everything. So we will be working on the adoptions. We will be working what I learned. I actually want to get a hands over on that. everything. So that is something that I will be actively like getting into within a month or two. Okay.
Sure, sure. They
Yes.
want to see you once, if it's possible, before you start your lecture. Then you can turn off your, if it's possible. Otherwise, maybe
Oh,
tomorrow or day.
at the end or tomorrow.
Yeah, sure, sure.
Okay. Yes.
Right.
I think my screen is visible to all of you. When see the screen.
Yeah, now it is. Okay. Yeah.
Yeah.
You can.
So again, like those who attended my earlier lectures, you know that I generally don't prefer like slides. Whatever we will do, it will be live, and everything. What I will be writing in the this notepad, I will be saving it along with all the annotations and all, and that I will be sending you as a class notes. Okay. So that is how I want to proceed. So before starting with this thing, quantum correlation and entanglement, that is the primary thing. So I just want to like highlight a few things. It is very difficult to make it in a bi-directional way. That will take a lot of time. I will be doing that. I will be setting up some quizzes as well. But before starting with that, let me just, for those who attended maybe QT-05 for the very first time, so I will be starting with a free introduction. So I just hope, or I'll be giving you a quick review on the few of the like postulates and terms. I've seen like you just completed the quantum gates as well. So I just hope that. So I hope quantum superposition is something that you have very well alignment with, which we introduce it because you are in the middle of the course. So I'll not go that detailed. So superposition is the art or is the kind of facility that is being provided by a quantum mechanical system to be in multiple possibilities at the same time. That is what we are aiming for. Multiple possibility as in, say for example, for a 2-qubit system, it is a ket 0. I hope right now you know this represents, this means a ket 0, okay, and a ket 1, okay, together. So this is the essence of superposition, and this is for a 1-qubit system. So in a superposed state, how they will look like is, say I am referring psi as a superposed one single qubit superposed quantum state. Okay. So they will be represented like 1 over root 2 ket 0 plus ket 1. So this is a mixed state, right? This is a mixed state or a superposed state, you can refer. Superposed state. Okay. And this entire thing is also represented as ket plus. This is the same meaning. Ket plus means exactly the same thing. 1 over root 2 ket 0 plus ket 1. Second point to be noting here is, what is ket 0? It is one pure state, ket 1 another pure state. They are getting superposed. Okay. And what is 1 over root 2? This is the probabilistic amplitude. So quick recap I'm doing. This is a probabilistic amplitude. So these are not the probabilities, but why we are taking 1 over root 2? Because we are trying to normalize. And what's the background equation for it? That is, it is actually, you can understand, it's 1 over root 2 ket 0 plus 1 over root 2 ket 1. And the equation is, or the logic here is for normalization, root over of this thing whole square plus this thing whole square should be equals to 1. And if you notice, it is half plus half, that is root over of 1, that is exactly equals to 1. Okay. So also another point is, this is the topic number 1. Okay. So point is, the probability of getting or obtaining 0 is basically 1 over root 2, that is the probabilistic amplitude associated with ket 0 square of it. So this is half, which is 50%. Okay. And the probability for ket 1 is 1 over root 2 whole square. This is half. This is equals to 50%. So we call it like 50% probability to be in ket 0 and 50% probability to be in ket 1. Okay. Similarly, this is only for a single qubit system. If we go on or proceed with them some more number of qubits, say for example 2 qubit, 4 qubit, 5 qubits and all. Accordingly, the number of superposed states, that is the together how many states we can encode in the quantum mechanical system, that will increase, right? So superposition or quantum superposition actually brings into the picture of parallelism, or kind of the advantage or supremacy that we are talking about. So quantum supremacy, its advantage over classical, all these things that we talk about, all the hype around quantum, all of them are because of the superposition primarily. Primarily. Okay. Why? Because superposition gives us that kind of flexibility. Okay. For example, I always give the same example here. If we have a five finger, say in our hand we have a five finger, right? So if you just imagine your finger to be as a qubit, right? Now your each of your five fingers can be either up or down, or maybe up, down, down. Likewise, right? You can make your fingers like up, down, likewise. Now the concept of quantum is that you can imagine it in this way, that it is a qubit right now, and all the five ones are equiprobable to be in any of these states. Okay, so they are 0 or 1 product, 0 or 1 product, 0 or 1 product, 0 or 1 product, 0 or 1. That is 2 to the power of number of qubits. So in this case, it is 2 to the power of 5, that is 32 total possibilities we can encode only using 5 qubits. Okay, that is the thing. So that means starting from 00000 till 11111, so 0 to 31, all these 32 combinations or configurations we can encode using quantum superposition or using the principles of quantum, giving us the concept of quantum parallelism or supremacy or advantage. Right? Just keep a note on that. Second point to notice here is the difference between supreme, because we are introducing these terms. So supremacy and advantage. See, first of all, a lot of terms are going to be overlapped. It's quite obvious. So I will be covering everything that is needed for you to understand or have a detailed kind of grip into whatever you say, that kind of a feeling about quantum entanglement. That is what my aim is. Maybe a few topics will be related, maybe a few topics will not be related, but just keep your patience on that, because those who have attended, maybe like when we were discussing the quantum mechanical postulates, we have discussed something, or might be a few parts were missing. So today's idea is to cover the quantum entanglement and correlation, and whatever is required for you to understand it in a detailed way. That is what my aim is for today. Okay, and similar things will apply for like tomorrow and day after tomorrow. Tomorrow's will be on complexity classes, the classical ones. So maybe a few ideas will be different, but I will try to cover everything for you to understand the classical complexity in detail. So this is the idea between idea of quantum superposition. Now, as I was talking, what is the difference between supremacy and advantage? Just be very careful about it. Whenever in a paper or anywhere you are, or say maybe in a news feed you are getting like classical computers with respect to classical ones, quantum computing, or this particular idea has got some result to demonstrate quantum supremacy versus to demonstrate quantum advantage. How you should be identifying the difference is, supremacy is something where we are going to get some exponential speed up. Okay, so supremacy, the term supremacy is very much related to exponential speed up. Exponential, or it can be near exponential. Okay, I hope you understand that. Near exponential is just differing by a few constant terms. Exponential speed up. Okay, and for example, say n has now become log n. Okay, or maybe 2 to the power n has now become n, k to the power n has now become n cube, likewise, right? And advantage is when at least, say at least there exist, this is there exist one, okay, at least there exist an improvement with respect to the classical algorithm or method, whatever you say. Okay. So if there is an improvement, we will call it a quantum advantage. For example, say earlier we used to need 2 into n number of queries in our classical setup. In our quantum setup, it is going to take n plus 4 number of queries to get the correct answer. Right? So we call, since it is 2n plus 4, so after a certain break-even point, definitely 2n is going to be complexity-wise higher than n plus 4. Right? So we call then n plus 4 as a quantum advantage. Okay? I hope this is clear. These are few words or few concepts. It should be crystal clear in you. Now, the second topic or the most important one here is the next one. So, remember the primary mileage that we can get in quantum is from the quantum superposition. That is for sure. The second term that we need for us who are focusing on the computing part, not only the physics or the mechanics part. The second one is we need the quantum entanglement. And this is what exactly our topic of discussion is, and I will also mention like why I specifically have talked about the superposition ones. But before getting into quantum entanglement, again a few knowledge check I want to give to you. I again imagine or hope that you have a good knowledge on Hadamard gate, which is 1 over root 2. I'm just writing the 2 cross 2 Hadamard. 1 over root 2, 1, 1, 1 minus 1. This is a 2 cross 2 form. So this is used in superposition, which does this. So Hadamard is an operator. This is a Hadamard operator. And whenever it is operating on ket 0, it is actually giving you 1 by root 2 ket 0 plus ket 1. Similarly, Hadamard on ket 1 will give you 1 over root 2 ket 0 minus ket 1. Since you just have finished the quantum gates and circuit, I think this is should be crystal clear to you. Right? So, and the math behind it is basically ket 0 is a column vector which is 1 0, and Hadamard is nothing but, as I mentioned, like 1 over root 2, 1 over root 2, 1 over root 2, and minus 1 over root over of 2. This is a matrix, right? So Hadamard on ket 0 is nothing but a matrix multiplication of this 2 cross 2 1 with the product with 1 0. So if you check that, it will be 1 by root 2 into 1 plus 1 by root into 0, that is 1 by root 2. And here 1 by root 2 into 1 plus, so this is also 1 by root 2. So if you take 1 by root 2 as common, it will be 1 and 1. Now we all know that this part represents the 0th one, and this is for the 1. I'm not writing first, I'm writing 1th. Okay. So that means this is 1 over root 2. This is for ket 0 position, that is a 0th position. This is a 1th, say for example, position. So this is nothing but ket 0 plus ket 1. So this is a superposed one, right? And Hadamard is used for that. Just keep a note on that. Second gate that I expect all of you to know is the C not gate or the control not gate. Okay, this is a control not. Why it is not? Because it is an inversion. And why it is controlled? Because it has certain controlling or control signal. Say for example, we better call it a control qubit. So whenever there is a control, there has to be some target. So the truth table of it looks like something like this. Say the the inputs and the outputs. So this is control, this is target, this is again control, target. Like the fate before and fate after C naught. Okay. So this will be initially, if it is a 2 qubit gate and two variables are there, control one and target is another one. So there obviously will be 4 combinations for that. So 0, 0, 0, 1, 1, 0, and 1, 1. Now the logic works in this way. If the control is 1, then it will be flipped. Otherwise, there will be no change in the target. Right? So in that case, it will be something like, so control 0, nothing, no change on target. Control anyway is going to be same, first of all. But if control is 0, there is no change in the target. But if control is 1, target will be flipped. That means 0 will become now 1 and 1 will become 0. So this exactly is the truth table for your CNOT gate. And in a quantum circuit, how it will look like is in this way. Okay. The field circle, this means a control, and this one represents a target. So if you just see this part, or say what to say, part of circuit, say for example, or circuitlet in that way, so it will be ultimately from the circuit itself. You should be understanding that this is a CNOT gate, and whichever is on top bits Q1. So Q1 is your control qubit, and Q2, this one on where you can see the plus sign or the XOR kind of symbol, it is your target qubit. Okay, so these are two things that you should be knowing. And also very important, like one gate I want to talk about, or two gates, are Pauli matrices or Pauli gates, where primarily I want to talk about X and Z. So simply X is the inverter gate, does nothing like 0, 1, 1, 0. If you apply X on gate 0, it will make it gate 1, right? And if you apply X on gate 1, it will make it gate 0. No change. And the Z is the phase gate. How much phase? Pi. So it matrix looks like 1, 0, 0, minus 1. Where the minus 1 have come from? It comes from the e to the power I pi. Okay, it's cos pi plus I sin pi, and from that we got it's basically minus 1 plus I into z, that is minus 1. So from there we got the minus 1. So 1, 0, 0, minus 1. Now whenever z is applied on gate 0, it does not make any change. It is again as it is. But whenever z is applied on gate 1, it will make it minus gate 1. That is, phase of 1, gate 1 will be shifted, phase shifted. Or we can also say it is a phase flipped. So X is responsible for bit flipping, and the Z is responsible for phase flipping. Okay. So what we talked about is the basic essence of superposition. Then all the like few basic gates like Hadamard, C naught, X, and Z. Okay. So I just want to have a quick pause here. I just want to understand. Just a minute. Let me take some questions. Is there any question that I can answer right now? Okay. Anyone has any question, you can put it on chat as well. Till this part, is it perfectly fine for everyone?
Yeah, participants, if there are any questions, please post in the chat. Otherwise, we'll proceed further.
Yes. All these instruments are going to be applied. That's why. Okay. I will be going. Why I have not like mentioned the Y gate? That will be part of it because Y is not something that directly comes after measurement. So that I will cover. Okay. Sarita, I think you are, I think supremacy advantage, I already discussed about it. I will be discussing about, today's topic is on entanglement. So I'll be definitely work topping, like talking about what are the applications, where we can use it, how we can identify some use cases for that. Everything I will be discussing about. Okay. Whatever I covered, there is no question, right? From the technical details. Class notes will be, okay, I got it. Thank you. Thank you. Okay, class notes will be whatever I'm writing here. So I will keep these things. These exactly you are going to get. And also the recording will be there with you. Okay? You can refer that. Okay. Let me just go back again. So with that particular kind of thing, understanding, we can now proceed or exactly formally enter into entanglement. But before getting into entanglement, there is another word which is called correlation. So those who are working on the machine learning and all, we are actually well aware of the term correlation. To be very like precise about it is where there is a certain kind of a relationship between multiple variables or both variables, say x and y. If there exists certain kind of relationship, okay, we call it a correlation. That x is correlated to y as well as y is correlated to x, which also can be extended little in this way that both the variables or one of the variables can determine the fate of the another variable. Very simple example. Let me just cite here. No quantum, purely classical. Say for example, I have a left glove. I have a box A and a box B, right? So say left glove. Let me just write it in this way. Left glove I have put in box A and the right glove, hand glove, I have put in box B. Then I've shuffled the box. Okay. Bit of shuffling I've done. And I have sent the box A to now. After that, I have sent the box A to Alice and B to Bob, for example. And there is definitely no communication can be possible between Alice and Bob. Now, the thing is that what will happen is Alice, say for example, is receiving the box A first and have no clue on what Bob has received. But still, Alice will understand immediately on receiving the left glove that definitely the right glove has been received by Bob. And there is no question of uncertainty here. Right. So here, basically, we can mark it in this way that the properties, all the properties are already fixed in advanced. And second one is measurement only reveals. Remember and notice here, we are focusing on reveals, meaning in classical correlation, if we measure one outcome, it does not any way do some tweaking on the other observation. Again, I am repeating, in classical correlation, we do not have that option. Say two variables or two objects or two physical entities are correlated. Then doing some operation on one does not really guarantee that or cannot really do any molding or any tweaking on what the second variable is going to give us. It has to be pre-rooted kind of. So it's very much fixed. So that means here correlation is coming from some pre-existing, notice here, pre-existing hidden information. For example, also like in machine learning, we have seen that if two variables are correlated, so some mathematical equation is there already between them, in between them. So we are just using a formula, say regression or something, in order to get identify that what will be the exact value. So the measurement will reveal the exact value, but here we are not anywhere doing anything on that. So this is correlation, but this is not entanglement. One is not really impacting the other. Only the measurement outcome will be different or they will be correlated. But this is not entanglement. When we will be talking about quantum entanglement, it will be again clear. So the left and the right are fixed beforehand. And here, correlation that you can see here, it's kind of a passive one. And also another point is here the local realism works. So remember, only point is measurement only reveals. That is the most important one. Local realism means, again, it is very pre-rooted, fixed, static, nothing you can do on the go. Got it? If one is something that is already done, set, whatever is the other one, that is already there in hand. Cannot do any change on that. Now, with respect to, or let me just give you another example. I'm not writing it. Say you and your friend received two dices. 1, 2, 3, 4, 5, 6. Both of you have received. And say, for example, it's made in a factory. Now, whenever your dice A shows even, dice B will always show odd. And say vice versa. Right? Dice A showing odd, dice B showing even. And you are rolling them in different cities. So here also, you actually can get what is the outcome. So my questions here is, in classical setup, do values exist before measurement? The answer is yes. You're not doing anything with the value. You're just getting the value, nothing else. So the values definitely, that means, should exist before measurement. Measurement is not doing anything on that or has no role on creating the value. Second is, can it be explained by the hidden information? Again, the answer is yes. That is what we are talking about. But the question is measurement creating the outcome? Understand the question here. Is measurement not only revealing, creating the answer? And so these are the dilemmas. Dilemma 1 and dilemma 2. Can everywhere this local realism be experienced? Well, for classical, both the answers are big no. Classical cannot do that. So now comes the quantum correlation theory, where the idea or the gloves story we were talking about, if it is a quantum gloves, so that means you can think it in this way that uh, whenever, say Alice and Bob, and you are using qubits, okay? So qubit can be, say a superposed qubit you have. So it can be either a 0 or a 1, but what it is, you don't know that. But definitely, the arrangement is in this way that if Alice gets a, say, head of the coin, then Bob will be getting a tail. Or if Bob is getting a head, then Alice will be getting a tail. Okay? So the thing is, the logic, the quantum twist of correlation can be thought of in this way that neither coins are head or tail. It's not pre-rooted. Okay. Second is they are in superposition. So the first point that now you should be noticing here is for entanglement of two qubits, you have to have superposition there. Otherwise, you cannot establish any entanglement theory. Okay. If two qubits or if one qubit or whatever it is, multiple qubits, they are not in superposition, then entanglement is not possible to be imposed on them. Right? That is why we talked about Hadamard, we talked about the supremacy advantage and all the gates, the pure state and the mixed states, all those things. Mathematical derivations will come now, but understand. So if quantum correlation or quantum entanglement has to exist, they have to be in superposition. First thing. Second is neither of them are pure ones, of course. And the third one is the result is not decided in advance. How to decide that? Because you neither know the outcome one as well. You don't have any knowledge on the outcome one. What you are claiming is your outcome one and outcome two will be some way quantumly correlated with each other. But what you do not know is what exact outcome your outcome one is giving to you. What is the value? That is not shown to you. That is not given to you. This is the theory of entanglement, right? Or quantum entanglement. Now, again, before jumping into the mathematics, I just want to discuss a bit of theory here from Einstein. So, Einstein basically negated this. He couldn't believe that this could have happened. So, Einstein's objection or observation here was that if two objects are separated by a space like distance, okay, let me describe that, then I'll be giving you the notes. So, if two objects are separated by a space like distance, meaning space like distance means something that cannot be time traveled. Okay. So, in that case, that is in reality, you cannot actually make it happen. There is a space like distance you can think it of. Cannot be time travel means even time, even with the speed of light, that cannot be made happen. So that is why kind of an impossible theory. So if two objects are separated by a space like distance, a measurement of qubit 1 should not affect the state of qubit 2. Okay. So in that case, the Copenhagen interpretation or the very basic, the primary interpretation of quantum mechanics that we have, he actually negated that. So let me just write it down. So Einstein, let me write it down here. So Einstein, first, Einstein's say objection here was that this is very important. We are heading towards the EPR paradox. Okay. So this is a paradox. Why EPR? Einstein, Podolsky, and Rosen. These are the three scientists. So all three of them came up with certain objection that okay, no, this cannot happen. This is impossible theory to happen. But later, they actually also came up with that okay, their intention or their objection was wrong. It actually showed that it could happen. So that is a theory. So Einstein's objection was if two objects are separated by a space like distance, meaning that a distance that cannot be time traveled. So in this case, if two objects are separated by a space like distance and they cannot be time traveled, then a measurement of, so it will imply that a measurement of qubit 1 should not affect qubit 2. There shouldn't be any influence, right? But again, in 1935, basically, all the three scientists, E, P, and R, Einstein, Podolsky, and Rosen, they published a paper, that a paper questioning the interpretation of quantum mechanics, and later they claimed it as a spooky action at a distance. Spooky means, you know, all know, something which is not very like common or casual, or some ghost behavior is there. So it's a spooky action at a distance. And their theory was there is a spooky action at a distance type of correlation between two particles, irrespective of how widely they are separated. Okay, so here is where the like fantastic points or the world or the magic of quantum comes into picture. You cannot really predict what is going to happen. That is why it doesn't obey the Newtonian mechanics and all. It's a quantum mechanics. It's pretty different than what you can imagine of. So the thought experiment, which points towards this inadequacy or the incomplete description. Okay, let me write it down. So the thought experiment pointing towards the inadequacy, meaning the incomplete description. I hope my handwriting is kind of interpretable by all of you. Otherwise, you can refer the like this lecture as well or the recording as well. Towards the inadequacy of quantum mechanics was the thought experiment pointed towards the inadequacy was actually what we call or what they call as element of physical reality. Element of physical reality. So, according to his quote, if without in any way disturbing the system, let me just write his quote on the entanglement theory. So, remember, this is Einstein's quote or on EPR paradox. Okay, it was if without in any way disturbing the system, we can with or we can predict, say, with certainty certainty means it's a probabilistic term that is with a unity, right? That is with probability of unity. Okay, that is if any way not disturbing the system, we can predict with certainty the value of a physical quantity, then we will say there exists an element of physical reality. I was writing here, I guess. Yeah. Element of physical reality with respect to the corresponding entity, physical entity. Wordings should be like same or at least like meaning you should be understanding. Since I'm referring it as a quote, maybe one or two words, you just double check that before you actually use this information anywhere. So, meaning that if again, what do I mean by like without any way disturbing the system? So the theory is here the measurement and the preparation contextuality. What is the theory? The measurement and preparation contextuality. I will not get into a lot of it. These are theoretical again. So I will rather prefer you showing the quantum circuits or application side of it, but at least understand that in quantum it is not possible if you are having that entire contextuality, meaning the understanding of the context, how you prepared it, what are all the values, what is the probabilistic amplitudes that you can think of. Then in measurement, you do not have any control about. Or if you want to control the measurement, that you do not have any control on the preparation level or how individually the Hamiltonian is getting evolved with course of time. A lot of terms, I hope right now in QT-05 you should be understanding it, but just understand there is a paradox, there is an imbalance between the measurement and the preparation here. And this is exactly was the notion behind Einstein's theory of or negating the entanglement theory. Okay, but again later what he came up with was it happens and it's a kind of a spooky action at a distance. So the entanglement, now let us get into the mathematics part of it as well. So entanglement, I referred that it has to be definitely a superposition element here. So how it looks like, now comes in entanglement the theory of maximally entangled quantum states. So maximally entangled means entanglement can have a different kind of idea, but mostly you can think it of a balanced 0 1, or there is a certain kind of, say, the density wise, if you proceed, it will be the maximum unbiased system. You can think it of in this way. Okay, the unbiased between the number of qubits or the phase or the like bit, they are maximum. It's very well distributed, kind of that. So maximally entangled quantum states, also known as, in simple words, entangled states, also known as Bell states. So we have four Bell states, right? The first one is this thing. Okay, everything you know it's here represented as psi and phi. So phi plus is basically 0 0 plus 1 1 by root over of 2. Phi minus is 0 0 minus 1 1 by root over of 2. Then psi plus is 0 1 plus 1 0 by root over of 2, and psi minus is 0 1 minus 1 0 by root over of 2. Okay, now we will be looking into how to construct all the circuits and all, right, where we actually will be needing the concept of quantum gates that we just talked about. So let me just take this one. We will start with, say, of course you can understand this is qubit 0, or say qubit number 1, this is qubit number 1. These kind of notation wise understanding should be very very clear to you to refer anything new. This is q2, this is q2. Don't get confused as this is q1 and this is q2, right? Individually you have to think of they are in superposition, right? Similar things will apply for this and all the like three remaining Bell states as well. The idea, the notation will be same. So first targeted to construct phi plus. This is our object, right? Now there are two qubits we have identified. Without two qubits, there cannot be any entanglement. If I have to have some correlation with someone, then that someone should also exist. I alone cannot make any correlation. Likewise, here as well, at least minimum number of qubits for entanglement has to be 2 or more than that. Now, if it is 0 0 plus 1 1 by root 2, let me start with q1 and Q2. So Q1 will be, okay, if nothing is mentioned, you should be knowing by now that it is actually 0, if nothing is mentioned. Otherwise, if we want to make it 1, then from gate 0, we have to apply a NOT gate over here. Right now, we don't want to do anything. So by default, they are initialized with 0 and 0. So now Q1, I will be applying a header mod gate. You have your kiss kit, so these are the same things, right? Applying an header mod. And then output of header mod I will be taking. Output of header mod I will be taking, and I will be applying a C0 gate over here, where this is the control, this is the target, right? Okay. So these two qubits will be entangled. Now let me just show you why this happens. The deduction. So Q1 and Q2 initially was gate 0 and gate 0. Now what I'm doing, let's I prefer this. So for example, after this, what I'm doing, I'm applying a header mod. On what? On qubit 1. So from this, header mod on Q1, that is this qubit, will make it gate 0 plus gate 1 by root over of 2. And second qubit is no operation, so it will be as it is. Right? So this means, alternatively, I can write as gate 0, 0 plus this 0, 0 and 1, 0. And also remember, you cannot really make it 0, 0 plus 0, 1 because the position or the, it's kind of a vector one, right? So also keep a like note on the ordering as well. Now what we are applying, we're applying a C naught. What is the control of that? Q1. What is the target? Q2. So let me apply a C naught. Q1 being the target, Q2 being the, Q1 being the control, Q2 being the target. And here also just like a function, the sequence of arguments also matter. So this is your control and this is your target. You cannot make it Q2 and Q1. If you do that, it will be inferred by a quantum computer like Q2 is a control and Q1 is a target. So you have to be also like very cautious about that. Now, if you do that, it will be like, again, as I repeat, 0 will not do anything. So it will be 0, 0. This one will be 1 and 1 by root. Right? So this is the first Bell state that we have constructed. If you want to check it in lab or in your computer, how you can do that? Simple. If you are using IBM Qiskit, just use the drag buttons to create the header mod and the C0 ones. We'll be noticing everything, right? Or also because right now everything is very automated. Or if you want to write the code or want to verify the code, I'm just telling you what in the QASM format it will be. QASM means quantum assembly. It is actually influenced by the quantum computing language QCL, which was the premier or kind of primitive quantum language. Right now we have Qiskit, we have a lot of other languages. Okay, but Pikewill and all. But this is the like first version. So what you are going to get is initialization part. I'm just skipping. Very simple. You are going to get this, that H of Q1 and C naught of Q1, Q2. And of course, post that you are going to get the measurement amount. Okay. So these are the only two operations in order to do that. So in code itself, you are going to get that. Where it will differ, it might differ, the code itself. Maybe some programming platform they provide, they don't write header mod, they write something else. Maybe they just write the entire word like HADMARD, header mod. Or C naught is a control not for them, or CX for them. So accordingly, you have to adjust it. But the logic is same. See, whether it's represented like CX or it's represented like C naught or it's like control node. Similarly for header mod or H, whatever it is, the meaning or the logic is same. So in that way, we actually have constructed the first Bell state. Now let me also do one more. That is the second one. That is the 5 minus. I'll not right now take a lot of time, so I'm just assuming that we have this one. I will be starting from that, right? I already have that. So very easy this is. So from this, if you have to make this, what exactly, where is the change? Only in the sign, right? Now, from if you have a good knowledge on the quantum gate or library, or you will be having that knowledge, then you can map it very easily that this is the only qubit that is making a difference over here. So this is qubit number one, and from plus it is getting minus. That means its phase is being flipped. So phase flip related to the Z gate that we talked about. So immediately we just have to apply one gate, that is Z on Q1. If you do that, you will be getting 0, 0, minus 1, 1. Because why on this 0? Because this is 0, Z is not going to make any impact or difference, and this will be the gate. So the operations here will be H Q1, C naught, Q1, Q2, then Z Q1. After initialization and before measurement, just by applying this 1, 2, 3, these three quantum operations in this particular sequence, you are actually going to get the second Bell state. Right? Now, what I want all of you is right now to tell me likewise, like this, just write it on chat, the sequence of quantum gates that is required for the psi plus and psi minus. Okay, 0 1 plus 1 0 and 0 1 minus 1 0. Okay, I'm just stopping sharing. Everyone, just take 2 minutes of time. Just come up with that sequence of quantum operations. This is the first quiz you have. Okay, take your time, think about the quantum gates, what we discussed, and just come up with it. Yes, actually. Okay, meanwhile, I can answer a few questions. Dr. S. Ravi, the minus sign means the phase is getting changed. Yes, yes. If you notice the block sphere and all, I hope you covered that. So it's 1 is getting now minus 1. So entire the direction is going to change. Physical meaning of a photon is just the physical photon that we're talking about. The same theory from the photonics, the same thing here also. It is one of the quantum particles. Quantum also is coming from the word. Like rest of you, please do the quiz, complete it and let me know or write it down in chat. Others, I'm just answering a few questions. So yes, so and what I was talking, yes, so quantum is basically that is inspired by the word quanta or quantum, the plural and the singular form itself. So that means a packets of energy, and energy is nothing but again the photons, so they are the same thing. Okay, physical interpretation is exactly how you can imagine as a light particle. It has a particle behavior and the wave behavior, the de Broglie theory. So the safest one is what you can imagine as like a, say, an analog wave. Those who are from that communication part, you know that analog wave one and the sampling, quantization, coding. Okay, that kind of theory we know. So that is a wave theory, and say for example, the quantization and coding part is very much comparable to the particle nature of light as well. Just a comparison. That's what I want to draw. Yes, absolutely. I can see very fundamental questions, Dr. Chandrasekhar. Yes, absolutely, you are right. So classical computing is very much deterministic one because we are using mathematical model as an underlying system. And tomorrow we will be discussing about the Turing machines and all. So I will be detailing in a detailed way talk about the determinism and non-determinism again. But that is the logic. Classical computer is unable to handle the non-deterministic nature. Quantum can do that. That's why we call it non-deterministic or probabilistic. Because non-determinism explores a lot of paths. A lot of path means a lot of probability is there associated with every path. Kind of similar notion. We will be discussing about that. But when we measure it, it collapses to 0 or 1, then it becomes deterministic. Absolutely, you are right. So our task or the parallelism, supremacy, whatever we are talking about, we have to explore it. We have to actually use it, apply it before we measure. Once we measure it, then the power of non-determinism of quantum will become purely classical. That's absolutely right. Correctly identified. I think minus I have just talked about. Don't worry a lot about Hamiltonian of okay. So many good questions I can see. Just a minute. Okay. Anyone has got any answer? Pauli X and Pauli Z. Okay. Please mention just also one thing. Please mention that whether it's the third one or the fourth one. So we can just write the Q3 hyphen the instructions that we want and Q4 hyphen the instructions that we want, and do that. Yeah. The next question is what I have seen is Hamiltonian of any quantum circuit. So don't worry about Hamiltonian. Hamiltonian is exactly the way your quantum system evolves. So quantum circuit or executing the quantum circuit is itself like solving every Hamiltonian one by one. Same thing. Say for example, you are just tracking your say what to say your body. You have to track how many what are the things that you are doing. So maybe right now, or say you are actually waking up at 8 in the morning, then you are taking some food. So maybe your BMI will be increased. Just an example I'm giving. After that, maybe you are working out or doing some gym or walking or reading something that will actually tend to some calorie burn. Then you will be in a phase with say some 50 or 100 grams you have again lost. Again you are eating something, you are gaining, again losing. Likewise, so your body is evolving. And how it is evolving with respect to time, and through what it is evolving with respect to certain foods, say for example. So similarly here, your body is a quantum circuit or a quantum system. Both are interchangeably, they can be used. Food is the sequence of quantum operations, Hadamard, C naught, C phase, XYZ, all these operations. And at similarly, like at say 10 a.m., I'm getting into your body or checking all the parameters. Then at after that at 12, all these things. So at 10, what I'm measuring will be your Hamiltonian at 10. At 12, if I'm measuring it, it is your Hamiltonian at 12. Okay. And all these Hamiltonians are being governed by the Schrodinger's equation. That is how it is taking place. So the time evolution of quantum states is simply the Hamiltonian, nothing else. It is not anything like direct any gate exist or Hamiltonian of quantum circuit is something that you can calculate or tell me. It's not like that. Okay. Okay. How to represent C and T on line with C equals to 1 and or C equal to 0? How to present C equal to 1 on circuit line? You cannot do that. Cannot do that. You cannot exactly make it like C equal to 1. C itself is a gate. Now, if you want that initially that line should be mapping to qubit 1, not qubit 0, that you can do by incorporating an X gate on that qubit line. But you cannot change that. You cannot make it like C equal to 1 on the control, because it is already embedded. Whenever your control will be getting the value 1 from the earlier operation, because remember entanglement cannot work without superposition. So from your superposition, whenever it will be getting some value 1, it will be on, it will flip the target. If it is 0, it will not do anything. Okay, there is no manual control on that. Superposed, okay, I think can ignore this. How this an advantage is not in terms of classical gates, it is in terms of, let me just see other questions. Okay.
Ma'am, some questions are, I think, directly addressed to you. So please read out the question because they are not here. The screen is not visible because madam is discussing the queries only. Okay.
Okay. Yeah, let me just share it.
Yeah, some questions may be directly, when it may be a private chat with you. So you read the question and give the answers. I think that will.
Okay. You can put it here itself, I think. Okay.
Yeah, please post it in the open chat so that it'll be easy for others also. They will get benefit. Okay. Thank
Okay.
you.
Yeah, I was just discussing it. Okay, I thought it's visible for all. Um, Sir, where I can get the, is this the direct one? The other questions, or whoever has like asked those questions, can you also like post it here? Mm, and do that.
Yeah, I think some question you are reading, actually it was not there in this. Anyway, that's okay, ma'am. Then you can continue. No problem.
No, I am
Please
actually
post.
referring everything that I can see in the everyone, like that
Right,
the
then that's
big
fine.
group.
That's, yeah,
Okay. Anyway,
right. Please go ahead. Yes.
yes. Okay, I think all of you are done with Hamiltonian is one. Okay, I answered this one. Let me just check it. Okay. Okay. Mm, I will do that. I will do that. Once like all three classes will be over, I will be doing that. Three topics are very different, so let me just cover it. Then on Friday, I will be doing them. Okay. Let me again, I think all questions are solved. If you have any questions, whenever we will be discussing on the next quiz, we will again be coming here and solving everything. Yes. So the third one, can just have a check on that. I'm a little quick on that now. So this is, let me do this. Okay, the fourth one. This was 0, 1 minus 1, 0 by root 2. So we will be starting with 0, 0 plus 1, 1. We all know now how to do that. After that, there is a bit flip here, right? So it's a x on qubit. Which qubit? Qubit 2. So x on q2. So that means it's a h on q1. Then it's a c naught q1 q2. Third operation is x on q2, right? So this is 0, 1 plus 1, 0 by root 2. Next is, this is the third one actually, psi plus, okay? And for the fourth Bell state, you just again have to apply a Z gate, right? On Q1. So that will give you. So these are the sequence of operations that you have to do to construct the Bell state, right? Now, I hope all of you have checked it and absolutely okay with it. Okay. Now the next is another gate. Let me just talk another Bell state. And before that also let me just discuss. See, 0, 0 plus 1, 1. Try to understand the fundamental difference. What says 0, 0 plus 0, 1 by root 2. These are two things. Both, though, like they both seem to be an entanglement. Okay. But this is a maximally entangled one, but this is not. So this is not entanglement. Why? Because you can easily decompose it or make it a independent one. How? This is ket C. Qubit 0 are similar in both the ones. Qubit 1 is being different. So we can make it like ket 0 product ket 0 plus ket 1 by root 2. Just cross check it. This is the same state. So whenever they are separable, there is no entanglement. But in this case, they are not separable. So that is why that is an entanglement. Okay. Likewise, you can check. Another entangled state example is the gigahertz state. Okay. How it looks like, say for example, I'm just making it as this. I can name it as I want to. So this is ket 000 plus 111 by root. How to do that? How to do that? Okay. So 1, 2, 3. There are 3 qubits. Right? Should I be applying Hadamard on all of them? Okay, a quick question. Immediately. Next quiz. How to construct this one? Because you already have worked on the quantum gates and circuits. I think yesterday or day before yesterday. Understand my question. My question is, how many Hadamard I should be using in order to create this particular quantum circuit? How many Hadamard I need? Okay. Uh, okay, just a minute. Yes. Please put your answers on chat. How many Hadamard I need? Okay, one answer, two. Two Hadamard. I have 3 qubits, if you remember. Okay. Uh, so I'm just taking the unique answers here. 2 and 3. Anyone? Any other thoughts? 3. Maybe 6. So 3, 2, 6. 10 more seconds. Anyone wants to come with any other solution? 4. 3. 3, 2, 4, 6. Okay. Let me pause now. Let me show. What is n? Don't write n. I have 3 qubits. You know the states. How I can do the coding with n? Okay, Rohan got another one. 1. Good. 8 states. No, you can see only 2 states. Okay, got it. I got it. I got all your answers. Manish. So Rohan and Manish only actually get the correct answer till I observed. So see here. That is where the magic of quantum comes into. We don't need a lot of concepts, but every concept should be very detailed, clear. We only need one quantum circuit, guys. Why? Because we have only root 2. You can notice it in different ways, but see, the probabilistic amplitude is only associated with this is the first one, this is the second one, and only Hadamard on one qubit can give you this root 2, nothing else. Means like, I mean 1 by root 2. Okay, so it will only be applied over here, and remaining are nothing but this. So a lot of questions were there. 8 states. No, it's not 8 states. What are states? How to identify it? This is state 1, this is state 2. So there are only 2 states. So observations are there exist 2 quantum states in the gigahertz state. Gigahertz is one superposed state combined, okay, consisting of 2 quantum states. Next observation is number of qubits. So number of qubits is basically 3. Qubit 1, qubit 2, qubit 3. Similarly, here also it's qubit 1, qubit 2, qubit 3. This is observation 2. Observation number 3 is number of Hadamard. So number of Hadamard will be only 1. That means there is only one state which is in superposition. Remaining are only entangled. Okay. So let me just show that. So initially they are 0, 0, 0. 0, 0 and 0. This was a first one. Now introducing Hadamard on, okay, and this is Q0, Q1 and Q2. I'm just marking it starting from 0, so that's 0, 1 and 2. So now I'm applying Hadamard on Q0. So this will make it Ket0 plus Ket1 by root 2, and these will be as it is, no change. Okay. If we have used 3 Hadamard here, then it would be 1 by root 2, 1 by root 2, 1 by root 2, that is 1 over root over of 8. And those who Right now I'm not going to discuss it, but those who attended, I guess, the interference topics, which I also, I guess, covered or someone else had covered, you might be knowing the concept of constructive and the destructive interference. So even if it is 1 by root 8, whenever we are deleting the quantum states or the possibilities, then what will happen? The amplitude, the probabilities and probabilistic amplitudes will be getting adjusted. That is the another essence of your interference, right? So it will be ket0 plus ket1 by root 2 only on first qubit I have applied it. Now secondly, let me just write it now. So 0, 0, 0 plus this 1, 0, 0 by root 2. Now it looks almost like similar, I guess. Now it's very easy. C naught on Q0, Q1 and Q0, Q2. So Q0, Q1 means first it will be 0, 0, 0 plus 1, 1, 0 by root 2. Then another, like you can do either like Q1 to Q2, either between these two, or you can do this because anyway they will be same. That is up to you. So it will be 0, 0, 0 plus 1 by root 2. So this is another entangled state that we constructed. Okay. So now what I want to talk about is the applications part. Let me just directly jump into that. So by now we have got the essence of entanglement, what it is, what are the minimum components like superposition should be there and all. What are the Bell states? How to construct that? What are the primitive quantum gates that we need for the say minimum entanglement to take place, which is a Hadamard followed by a C naught. That is, these are the two gates that are minimum set kind of thing required. All these we know. Now the thing is why we should be like superposition. We know for the speed up, right? Superposition is more aligned with the speed up, where entanglement is more aligned with. So applications of entanglement. First is it is used in the concept of random number generation. It's a quantum random number generation or quantum number generation, whatever. Say. Okay. Second is primarily in, of course, in quantum cryptography in terms of, to be very precise, it is in QKD, quantum key distribution. Third one is where in QKD protocol often might see in the BB84, ECARD 91. Okay, these are the protocols. B92 like this. And third one is a quantum communication, where primarily there are two components. One where entanglement is only the thing that is used, and that is your quantum teleportation, which cannot work, or kind of primary use case for entanglement, as well as dense coding. They are also again like more or less similar, but these are all the application areas. So primarily you can see there is an kind of an inclination of entanglement towards the communication and cryptography on this particular sector rather than directly, or unlike superposition, to be focusing only on the on your computing side. right? So, okay, I can do what I have thought of is, um, now again, I'm not sure if it is a like you have attended or in it or not. But what we can do is we can, because theoretically we are not left with any other thing, only if we want to cover entanglement. But one of the use cases that I just correctly right now mentioned, we can talk about that. So we can talk about quantum teleportation in a very detailed way. Why? Because it will give us few essence. First is the process itself, quantum teleportation, which is very, very important to understand quantum communication as well. Second is the application of Bell states and how to do that. Entanglement, how to measure it. After entanglement, how to measure it. And a quick brush up of all the quantum gates that we talked about, including the quantum circuit. Okay. So if you want, you can take a 2 minutes break or a 3 minute break. After that, we can start. And also, if there is any question, I just want to pause here for a little. If there is any question, let me just answer it. Then only we will be left today with the teleportation one. Okay. I think right now the your queries are over. How many Hadamard gets and all for the gigahertz one? Okay. First of all, let me just. Do you want any break? 2 minutes break. All of you want that? We have 30 minutes more, so we can take a break and come exactly at 4:30. You want that? Okay. A tea break or a water break we can take, right? Okay. Yes, I can answer few questions. Mm, correlation, entanglement, comparative. I think what you are asking is related to the classical versus quantum, if I'm not wrong. Maybe that is what you are referring, Rohan. Broader sense, in a very, very broader sense, you can take break. I'm just answering a few questions. Like correlation is a very broader way you can use it, more aligned with mathematical discussions or statistics. Entanglement is something that we precisely bring into picture for quantum purpose. And so yeah, so that's something I can do. And mathematically also, like quantum correlation and quantum entanglement, if you want in that way, more or less in terms of understanding, there is not much difference over there. But whenever you are referring only correlation and entanglement, I think, or you should be referring the classical correlation versus the quantum correlation, which again is a separately, you can coin it as an entanglement. That is the only thing. And whenever we will be taking or going into that thing, um, I think, yes, okay, okay. So whenever I will be doing the quantum teleportation, I think the that theory, the analogy will be even more clear. Detailed quantum communication, I don't know, Manish, whether that is included in the scope of QT-05 or not. At least not included in these 3 days. But yes, some essence you are going to get whenever we will be doing the teleportation. Definitely, we are going to get some essence of it. Let me now take 1 minute break. I'm just coming with some tea. Okay. Yes. We can start now. QML, encoding the classical. How entanglement enhance the encoding. I have to check that, Rohan. You can just separately on LinkedIn or somewhere. You can just detail mention if you're getting some paper and all. You can do that. Okay, I have to check that. But entanglement, maybe some you can notice it in this way. Wherever you can see a header mark followed by a C naught, definitely some sort of entanglement is there. So that kind of maybe they have just used that. Okay. Uh, okay, QKD, quantum secure authentication. Yes, these are all the like aspects, not the QKD one. QKD is a very standard protocol or approach, a generic one. Quantum secure authentication, quantum randomness, these are all the things that can be incorporated. Okay, these are very like detailed discussions need to be made for that, but a one liner answer will be for the question that Vikram, because you asked, is you can imagine the Diffie-Hellman key exchange protocol is not secure enough. Okay, so the key exchange part, the classical key exchange can be actually modified or can be upgraded to the quantum key exchange, and that exchange protocol is a quantum key distribution. You can think it of in this way. Or one another example will be, now anywhere wherever Diffie-Hellman is used, it now you can understand that now you can use the quantum that your that thing like QKD, BB84 protocol. And also one another one can be, say, quantum secure authentication. You can make use of a quantum random number as a key for that. So that will be quantum secure. Why quantum secure? Because again, a lot of discussions I will not make right now. It's a context of quantum cryptography and communication, but major essence here is like quantum random numbers or quantum itself is very much more secure than classical. So whatever you can do with a pseudo random number generator, if you replace it with a quantum random number generator, then the authentication or multi-factor authentication and all that can be made more secured. And because you are using a quantum underlying system is quantum, you are relying on quantum theory, so you can claim that it is quantum secure, something related to that. Again, a lot more discussions need to be done. Okay, I can start for some research bar. What to start with? Short's algorithm shows it can be break, absolutely, but Short's algorithm showed that the public key cryptography is broken. That's why. And so, if you want to start with that, you have to first go through the details of Short's and why and how it is breaking with the like quantum Fourier transformation. And also you can think it in this way, that is there any particular type of the algorithms that Shor is able to break, as I just mentioned, like the public key cryptography. So what are the things, what are the key elements or the patterns in that cryptographic algorithm which makes it breakable by Shor? Likewise, you can target or target and fix, of course, with quantum. Shorts is a threat. What we right now need is a solution. That's why we are thinking of the post-quantum cryptography, which will be inherently quantum safe and not breakable by any quantum algorithm as well as a classical algorithm. That is where we are heading, right? Okay. Okay. Can we start now? Can we start right now? Just give a thumbs up. Okay. Okay. Great. So we will be discussing about, yeah. So we will be discussing about right now on the or that one component of quantum communication where entanglement is for used for is a quantum teleportation. I will not break in between. More or less, it should be like we will be on time. I have a lot of calls after 5, so I have to complete it. Okay, so I'll be like completing it together. After that, we will be discussing on all the questions. So, what is quantum teleportation? It is a process of sending the process of sending one quantum state sending. We will decode more on the word sending. One quantum state from one place to another. Communication means we have to definitely make some transfer of something. So here that something is quantum state that you want to transfer. So point number one is, of course, in all the communication and cryptography, there is one Alice and one Bob. So Alice will be having this alpha 0 plus beta 1, and this is the desired state that Alice wants to send to Bob. So Alice has this, and she wants to send this to Bob. Okay. Now, before starting, let me also mention, if you want some other quantum circuit, you have to tweak some other quantum state, you have to tweak your own quantum circuit. This is only one example of teleportation to showcase or demonstrate that how to transfer alpha 0 plus beta 1 to Bob. A lot of elements are there. This is very complicated process. This is not very simple one, unlike classical ones. So we have to first must have a mastery on the art of like simple states. If we have to transfer, how to do that. That is what currently we are aiming for. Okay. And also we will be considering here, what are the considerations? So we will be considering Alice has no precise information of the state itself, which she want to send to Bob. Meaning, Alice cannot directly give any instructions to Bob so that Bob can also have the knowledge of what is the quantum state Alice wants to send. Alice has just some, say, intermediate quantum state. She does not know what is the values of alpha and beta. So it's an arbitrary quantum state to Alice that she wants to send to Bob. Okay, no knowledge about the state itself, even for Alice. Now, the catch is, the catch here is, when earlier, say, when earlier, I'm just writing A and B, meaning Alice and Bob met, they decided to share 1 qubit each. They decided to share 1 qubit each. And this is the, say, a Bell pair, entangled pair. So the thing is, Alice and Bob, it looks like this. So Alice and Bob share 1 qubit each of the Bell state 5 plus, that is 0 0 plus 1 1 by root over of 2. So this is the entangled state. Now what do I mean by they will share 1 1 each? Meaning, say 0 0 plus 1 1 by root over of 2. So, and Alice and Bob is there. So Alice will be having this one and this one. This is Alice's qubit, and say the dotted lines are Bob's qubit. There is a first qubit in this entangled one. The first qubits from all of the quantum states, the first qubit will be given to Alice, and the second qubit will be given to Bob. They will be sharing in that. So this is one entangled state from which Alice is taking a part and Bob is taking remaining part. Right? Now, on that note, let me give you the circuit for quantum teleportation. So, initially, what is the state that Alice wants to send to Bob? This is this one. So, this and here, these two lines. So, this is only one state, one superposed state. So, let me write state to be sent. Got it? Okay. And these two are the entangled belt state. So this initially will be a C naught gate, followed by a header mart here. Again, here I am assuming I have this gate, okay? This state, alpha gate 0 plus beta gate 1. I'm not constructing it. My target here is I have something already. This is arbitrary. I want to send it. So I'm starting my like journey from that point. Got it? So now this is a header mart gate. This is a line. Now say for example, I'm making a measurement over here. This is a measurement gate. You can see this particular symbol. Third qubit is one of the entangled qubit, and it will be, there will be a sequence of gates here, x and z, the Pauli x and Pauli z. And if this is psi, the arbitrary quantum gate. So this is what Alice, say for example, Alice has this initially. Bob, this is also Alice. Alice has this as well. Bob has this. Because Alice and Bob both are sharing one of the entangled qubits. And initially Alice has this psi state, alpha 0 plus beta 1. And this is the initial time. These are nothing but the quantum circuits, nothing but the time diagram. So this is initially, at initial time. And at end, it will be like here. So what is my target? This is Bob's dedicated line. This is not anywhere where Alice is having any kind of input over here in Bob's qubit. Okay. So this is where Bob here is. And what we want is, we want to successfully send the psi from Alice to Bob at the end of a few quantum operations. This is the main agenda. Okay. So, and because this is Alice, so this particular part is, till this part is Alice's encoding and measurements. Again, just remember, we are talking about quantum communication using quantum teleportation. What we are trying to communicate here, one quantum state, right? From one place or one user to another user. Nothing else we have done yet. Okay. Now let us see how it will work. So we will be applying Hadamard. We are applying Hadamard, right? So therefore, Hadamard on first qubit and measurement of both first and second qubit. Okay, so here also Alice has that entangled one, that is 0 0 plus 1 1 by root 2. Similarly, Bob also has 0 0 plus 1 1 by root 2, but no access on Alice's qubit is there with Bob. Similarly, with Alice, there is no access to Bob's qubit. Okay, that is the magic. That is the essence of entanglement. Let us see how it works. So, alpha, beta, these are there. So, I'm just, Hadamard is making ket 0 plus ket 1 by root 2. So, considering all of them, it will be ultimately this thing. Alpha, and this will be by root 2. So, I'm just taking it as common. So, ket 0 from this one into ket 0 0 plus 1 1 plus beta by root 2 ket 1 times ket 0 0 plus 1 1. This is something that we have. Now separately we'll do something, because Alice is on the first and the second qubit. That is the first qubit. This is first. Let me write. This is second. This is third. This is also second. This is third. Right? Now what I will do is, I will be extracting out only Alice's part. and keep Bob's qubit part separate. Okay. So if we do that, so let me write it down now separately. What's a separately extracting out Alice's part or keeping Bob's part separate, whatever you want to write. Equivalently, we can write it down equivalently. So what we are trying to do, we will make 0 0 together and third 0 will be separate. Likewise, it will be 0 1 together, then the third one will be separate. So just writing them down, it will be 1 by root 2 alpha 0 0 0 plus alpha 0 1 1 plus beta 1 0 0 plus beta 1 1 1. Same thing, just writing in a different way. Okay. Now, the C naught on Alice, whenever it will be applied, so this is Q1 and this is Q2. Similarly, this is Q1, this is Q2, this is your Q1, Q2. Third qubit, I'm not doing anything. I'm just applying C naught on first and second qubit. So this is Q1 and Q2. So now if we apply Alice's C naught, it will be 1 over root 2 will be as it is. Alpha 0 0 will not be any different. This will also be no difference because the first qubit is control. So no change. But here it will be 1 1 and here it will be, I think, 1 0. Right? Now this also means we can write it down in this way. Say same thing. I just want to show it to you that they mean the same. Plus alpha 0 1 1. Don't get confused with a lot of terms. Just minutely you need to break it down individually. Just look into one operation. Whenever I am doing thus from this I'm getting this by only a C naught. Okay. What are the fate of the other things? What are extra terms that you have to write? Don't worry about that ever. So this is 0 1 1 plus this is beta 1 1 0 plus beta 1 0 1. Right? Now, Hadamard, we know that Hadamard on Kate 0, what it does? Hadamard on Kate 0 will make Kate 0 plus Kate 1 by root 2, and Hadamard on Kate 1 makes it Kate 0 minus Kate 1 by root 2. This we already know. Right? Now, where your Hadamard gate is applied, it's applied on the first qubit, Alice's first qubit. Right? So let us just apply that. Let us just apply that. So also let me just copy this one. Not it 0 0 0 0 1 1. Okay, let me write it down. Alpha 0 0 0 plus 0 1 1 plus beta 1 1 0 1 0 1. Okay. Now before writing it down, I will do another small thing. I will just keep this 0 here and these two together. Why? Because on the first qubit only I want to apply the Hadamard. What will happen if I do that? It will just be a little simple for us to write it down or express algebraically. That's why we are doing it. Beta 1. I think, yeah, we have 8 more minutes. We can go. So 1 and then it's a 0 1. Now we are applying Hadamard on Q1. Alice is applying Hadamard. So it will now become alpha. This 0 will become Ket 0 plus Ket 1 by root 2. And this is as it is. Plus again alpha Ket 0 plus Ket 1 by root 2 1 1. Similarly beta Get 0 minus get 1 by root 2. And this is 1 0 plus beta get 0 minus get 1 by root 2 times 0. Okay. Now, by just taking alpha, beta, half, all those things, adjusting them, can we write it in this way? That taking common and all, that 1 by root 2, 1 by root 2 will be here. Nothing quantum here I'm doing, just few things like taking common, then managing it in that way. Just remember the sequence of all the qubits, because they are the vectors itself. So that also is very important. You have to keep a track on that, nothing else. So we can alternatively write it down as 0 0 meaning they're not commutative, that is what I'm trying to say, plus this will be 0 1 into alpha 1 plus beta 0 plus 1 0 alpha 0 minus beta 1 plus 1 1 alpha 1 minus beta 0. Okay. Now what will happen is, now this entire thing right now is the fate of the entire Hamiltonian. Whatever is there, this is encoded in this like complex equation, quantum equation. Right now if you very carefully notice, see 0 0 0 1 1 0 or 1 1, they can be separated, and the state also right now itself you can notice that alpha 0 and beta 1 are the is the particular state that we wanted to transfer. So the correct value alpha 0 plus beta 1 is associated with 0 0. Alpha 1 plus beta 0 also need a little modification, but it also looks very similar, but we need some operation with that. They are associated with 0 1. Similarly, some phase change had happened with 1 0, the coefficient 1 0, because it's alpha 0 minus beta 1, and similarly for 1 1 as well. Now what they have thought of is, till this part everything quantum. Right now what they are trying to do is, Alice has thought or made up his mind that after this, from here itself actually I will be sending. So this is a classical channel. Okay, so that means from this, whenever from exactly from this state, whenever Alice makes a measurement, okay, she can get either 0 0 or 0 1. Why? Because this is the first qubit, this is the second, this entire thing is the third. Don't forget that this is first, this is second, this entire thing is third. Likewise it goes on. Alice has access or hold of only the first and the second qubit. Bob has access on the third qubit. So even in this particular scenario, if Alice wants to send something to or Alice has certain information about, is only on the first and the second qubit, which can be, if Alice tries to measure, either 0 0 or 0 1 or 1 0 or 1 1. That is the possibilities or the 4 possible outcomes that Alice can measure. So let me just write it down. So now whenever Alice makes a measurement, she can get either 0 0 or 0 1 or 1 0 1. Right? Now, depending on what Alice gets, what Alice will now do, Alice will now pick up a classical channel. What do I mean by a classical channel? It can be a telephone, it can be some other means as well. Okay. Pick up a classical channel, maybe a telephone, and tell Bob what she got. For example, Alice will just make a call to Bob and just refer that, okay, hi Bob, I have just received 1 0, or hi Bob, I have received 0 1 or 0 0 or 1 1. Now Bob has received already something, alpha 0 plus C. Now Bob also have received this thing, right? Okay. Or he can, get these things if he tries to measure. Whenever Alice is telling that, hi Bob, I've just got 0 0, now Bob will be having a set of operations with him. Same set of operations. Similarly, he will be applying so that ultimately, if it is a correct one, then it's very good. If it is not, then the incorrect portions or the errors will be adjusted automatically by Bob. For example, if you just notice the circuit, it's a X and a Z gate together. Let me just quickly give you that. So, say Alice got this thing. Say Alice is telling Bob, I got 0 0. Now, what Bob has received? Alpha 0 plus beta 1. That means no operation. Nothing Bob has to do. Already it's a hooray. He has got the one. Now, say Alice says, this is case 1. Case 2 is Alice is claiming, I got 0 1. Okay. Then Bob has received alpha 1 plus beta 0. Whenever Alice says this, Bob will be applying an X gate. That's a flip gate. So 1 will become 0 and 0 will become 1. So rectified. Third case is if Alice is telling 1 0, then definitely Bob has would have been received so far this thing. So he will be applying a Z gate, a phase gate. 0 will be as it is, and this will be minus of minus beta 1, which is alpha 0 plus beta 1. Again, restored. And similarly, if Alice has received 1 1, so it is definitely then alpha 1 minus beta 0. So first he will be applying a what gate? He can apply anything, say a X gate. So it will be alpha 0 minus beta 1. Now we are in the third case, so I will be applying another XZ gate to get alpha 0 plus beta 1 finally. So therefore at the end, what we have achieved is, I'll just take 2 more minutes to conclude it. So at the end, Alice and Bob both have started with a state, actually both used this 0 0 plus 1 1 by root 2, and right now Bob has got the state at his end, which is alpha 0 plus beta 1, which Alice wanted to send. But now thing is, if you notice very carefully, does it mean that we can actually clone a quantum state? I will be ending with this open question to all of you. That is quantum teleportation. Question is quantum teleportation, if we are successfully able to send any arbitrary state, that means right now, can we just relate it with the concept of creating a quantum state? So is quantum teleportation violate the age-old concept of no cloning theorem, that a quantum state cannot be cloned? It's a question. Try to get the answer. Tomorrow, before starting with the complexity classes, we can actually have a discussion on that. But one thing is for sure that you right now you have the thing, I have that kind of state at Bob's end. So theoretically, the teleportation process is over. But the question is, does it mean that we actually are violating no cloning theorem also? Because if we are using quantum, that means we shouldn't be able to replicate any quantum state. So are we really replicating it? That is what my question is. Okay, we're on time. We can end it. If you have any question, you can just put it. 1 or 2 minutes we can spend on that. Anyone has any question on that? What I will just request all of you is, because those who are attending teleportation or this particular topic for the very first time, please refer to it again at your end. Once again, do all the steps, try to check all the steps, and then it will be a better understanding, because it's a very new concept. Okay, any question, or we can end here? Anyone has any question? Till teleportation it was all okay. Anyone has any question on teleportation? Great.
A good teacher will not have any doubts left.
We answered everything.
Yeah, in
Meanwhile,
between you have clarified many of the doubts. Yes.
yes.
Yeah, there are some questions.
Cloning, no. Okay, one clue I can give today, that it is, we are definitely, teleportation is also very fundamental concept, as well as cloning, or no cloning, to be very precise. So we are not violating. So what exactly is the missing piece here? So again, it is not violating no cloning theorem. We are not cloning it. Okay. Now, question is, why am I like telling that we are not cloning it? If it is not cloning, if teleportation is not cloning, then what exactly we are doing? Okay. And how exactly it is different with cloning? Okay. Just think about it. Tomorrow I will be starting with this answer. Then we will be proceeding. Where exactly difference in classical get output, truth table, and quantum get output? Give it one example. Of course. So I hope in quantum gates, whenever you had that concept of reversibility. So you can imagine it in this way, that say C naught. It is something. So all quantum gates are reversible. So from the quantum gate itself, you should be able to map what was the original inputs. It has to be that. Okay. And output, and if you notice, like C naught is a 2 qubit input, 2 qubit output. So whenever you have that information of the output, if you are able to get back to the input from the truth table itself, that how the like inputs were, then it is a reversible logic. And in quantum, all gates are reversible. For example, there is say not gate, right? The quantum not gate I'm referring. If you have 0, it will be 1. It's a bit flip. If it is a 1, it will be 0. Now, let me tell you the difference. In classical, more or less, maximum gates, they are not reversible. They are irreversible in nature. For example, say my AND gate, okay? Logical AND gate. So if you have 0, 0, you will be getting a 0. Or if you have a 0, 1 or a 1, 0, then also in output, like 0 and 1 is 0, 1 and 0 is 0, and 0 and 0 is also 0. Now, if you, after application of an AND gate, if you just look into the output 0, can you exactly tell me what was the input pair? Was it 0, 0, or was it 0, 1, or was it 1, 0? Cannot do that. So that's why, actually, that is the motivation for which we have thought of shifting or bringing into picture the concept of quantum algebra and all these things, because we have to believe in the form of reversible thing. Okay. And in quantum, everything is reversible. It's time driven, right? If you just undo the operation, you are going to get that. But till you measure, after you measure it, you cannot do that. I hope your question is clear. Yeah, state of qubit is transferring from one to another. State of qubit is transferring. Actually, not exactly. It's not state of qubit. It's one entire quantum state it being transferred. Yes, you are partially true. It is only about transferring it. And also, if you have noticed, right now, Alice doesn't have any control on the alpha 0 plus beta 1. So I'm answering to what question I asked right now itself. Please focus. In cloning, when we can call it a cloning? Whenever there is a concept of the Xerox machine, right? So initially we have a paper, we are putting it in a Xerox machine or a cloning machine, if it is again replicating the same paper. So after cloning, we should be having two copies of the same thing. One is original one is a copied one. But if you very carefully notice the teleportation that we have done here, right now, after the process, only the quantum state that is not exactly cloned, they actually are being transferred. And through what means? Bob, with certain information from Alice, actually have recreated it. The X and the Z get all of them, Bob is doing at his end to recreate it. But it is not cloning. Why? Because when Bob has at the end alpha 0 plus beta 1, Alice doesn't have that. So it's not cloning. It's something that Alice had earlier, right now Bob had. Okay. But in cloning, we will be getting the cloned copy as well as the original copy. That is the answer. I think now it's clear. Okay. I have to end my session. Thank you, everyone. Thank you, everyone, for the class, for your patience and asking so good questions.
Yeah, thank you so much, ma'am. Thank you for the passionate lecture, I would say always. Thank you for that, and for so many doubts and so many clarifications. That interaction shows actually the interest of the participants also. And around 500 participants are there every day, and that is one good thing that is happening. People are, of course, some of them who miss, they are following on the YouTube as well. So thank you so much for your time. Tomorrow we'll meet at 3 o'clock. All of you, please be on time. So we'll start on time. You will have more time if you all join on time, right? Thank you so much, ma'am. Once again, we will meet tomorrow at 3 o'clock.
Thank you, sir. Thank you, participants. Thank you.
कितने हैं participants?